Welcome to another MECH 1000 video. Today we are looking at Unit 7 in the Blueprint Reading textbook, which covers a variety of topics. The first topic to introduce here are bosses and pads. So what is a boss and what is a pad? Essentially, a boss or pad is an area surrounding a hole that has increased thickness, typically to provide strength to that hole. So the difference between a boss and a pad is that a boss surrounds a circular hole and a pad surrounds a slotted hole. So it is typically, as you can see here, it increases the thickness or the depth of the hole, and in cast parts it's typically machined. These finished symbols here indicate the top surface of that boss and pad is going to be machined. So a pad which surrounds a slotted hole can be dimensioned in a couple different ways. And the way in which a slotted hole is dimensioned can affect its tolerance. So we see two examples here of dimensioning. One is to dimension the center-to-center dimension between the two end arcs, and then to also dimension the width of the slot. When that is done, in order to calculate the overall length, which is not given, as you can see here, it's in parentheses, indicating that that's a reference dimension. So if you wanted to know the overall length of the slot, you'd have to calculate that. You'd have to calculate that by adding these two dimensions together. And if each of them have a tolerance of plus or minus 1, then this calculated dimension accumulates each of those tolerances for an overall tolerance of plus or minus 2. If you dimension the center-to-center spacing of the two end arcs and a radius, and each of them have a tolerance of plus or minus 1, to calculate the overall length, you would have to take that center-to-center spacing and add one radius, and then add the other. And so that requires the use of 3 dimensions, so you end up with an accumulated tolerance of 3. So dimensioning the center-to-center length and width of the slot has less accumulated tolerance. Okay, moving on, the next topic is tapers. So many mechanical parts have a taper to them. They transition from a larger to smaller size, and so we need to be able to dimension the taper and calculate some dimensions based on taper dimensions. So one common way to dimension a taper is to describe its taper per foot, or TPF. So that's indicating that for every 1 foot of length, the size of this, and this is a truncated cone, these are diameters. This diameter is going to decrease by 0.75 for every foot of length, and it's starting off with a dimension of 0.800. So if we wanted to know what is the diameter at this end, we can calculate that based on the known information. So the first thing we want to do is we want to take this taper per foot, the 0.75 TPF, and determine how much taper there is per inch. So we just divide our taper per foot by 12. So 0.75 divided by 12 is 0.0625. That is the TPI, or taper per inch. And so the length of this object is 4 inches. So if we start off with a dimension of 0.800 and we decrease that dimension by 0.0625 for every inch of length, and it has 4 inches of length, then we take that 0.0625 taper per inch, multiply it by that 4.00 length, and we can see that it is going to decrease in size by 0.25. So if we then take the starting diameter of 0.8, subtract the taper amount, we get the diameter at the opposite end, 0.550. We can do the same thing in the other direction. In this example, we're given the small dimension, 0.500, and we want to know what the diameter is at the other end. It's 3 inches long and has a 1.50 TPF. So again, take the TPF and divide by 12 to get the taper per inch, TPI. Multiply the TPI by the length. 1.125 multiplied by 3 is 0.375. And then in this case, since we're going from the small end to the large end, we add that amount to find that the diameter at the large end is 0.875 inches. There are standard taper sizes that can be found in reference manuals, such as a machinery handbook, such as a Morse taper. Morse tapers can frequently be found on the spindle of a lathe or drill press, and they are numbered, like a number 1 Morse taper, a number 2 Morse taper, and so you would need to look that up in the appropriate reference manual to find the exact dimensions. Some other standard taper sizes include Brown and Sharp or Jarno. Again, you would need to refer to the appropriate manual or reference table to get exact dimensions for them. Okay, let's again practice our taper dimensions. If we know the large end of this taper is 0.750 and it has a 0.75 TPF, what is the small size? So we would take this 0.75 and divide it by 12 to get the TPI, and that would be 0.0625. And then we would take that 0.0625 and multiply it by the length of 6 to get 0.375. That is the taper amount. That's how much smaller this end is going to be compared to the large one. So we take our starting dimension of 0.750 minus 0.375. And what we are left with is 0.375. So that is the dimension A. Here we're starting at the small end and we want to calculate the dimension at the large end. We take our 1.50 TPF and divide it by 12. And so that would equal 0.125 TPI, taper per inch. Take our 0.125 taper per inch multiplied by 5 inches. and that's 0.625. And we're going to add that to our starting dimension. So 0.625 plus 0.625 gives us a total of 1.25. So that would be the dimension at the large end. Okay, moving on to the next topic. If you have a situation like this where you have a shaft and you're going to turn down on a lathe, most likely, the end of it so that it can be assembled into this hole, what can happen is it can be difficult to remove all of the material right there at the corner. You might leave a little bit of material behind, which causes a little bit of a radius right there. And that radius, that little bit of extra material right there, can actually cause some assembly problems. It can cause difficulty in getting this larger part of the cylinder to be flush up against this surface. So one way that you can prevent that from happening is to provide a neck, which would mean that you would turn this part down to its desired diameter, and then in a small little area here, you would turn it down even more. So you would reduce that diameter more, and that is what's called the neck. And so you're going from a small diameter to an even smaller diameter, and then stepping back up to the large size diameter. And that is going to make sure that you don't have any of this extra material here. And so it ensures that you can get a nice flush fit. If we were to take this image and kind of rotate it, you've got the small diameter, and you've got the neck, and then you've got the rest of the part. So you can just kind of draw a little smiley face on here, and you can see why that part is called the neck. So here we have, it's called a special purpose shaft, and we will answer some questions here as time permits. We'll answer as many of these as we can before our 15 minutes are up. What is the depth of the blind hole? So again, a blind hole is a hole that doesn't go all the way through a part. So the first step to answering this question is to locate the hole. And here it looks like we have a hole. And if we look at the hole note, it does indicate here a depth. It uses the abbreviation DP. Alternately, it could have used a depth symbol. But either way, it has a depth of 0.44. What is the maximum radius permitted between steps of the shaft? So the steps indicate here we have a larger diameter, and that steps down to a smaller diameter, steps down even smaller, and steps down again. And at those corners where it steps down, there is somewhere on this drawing indicated the maximum radius that is allowed. So we would have to look all over the drawing, kind of scan it. And then hopefully your eyes eventually come to this note right here, which is indicating one of those steps has a 0.03 radius maximum typical. So that means that it applies everywhere where the radius or diameter steps down. So the answer there is 0.03. And it looks like that's probably the last question I'm going to have time for in this video. So we will resume this practice exercise in the next one.